Okay, a very good evening to all of you. So, third week is the content of the third week is already discussed with all of you on the by the Rajesh Prasad sir. Okay, so we are going to discuss those things. What are the content that has been covered, and we will solve few questions in such a way that you are able to answer the assignment question that is available to you. Okay, so let's get started. I will close my video so that we have a quite good quality. Yeah. So what we are going to discuss today is regarding the group 3 content. Sorry, week 3 content of the crystal symmetry and tensors. Okay. So the list of the topic that has been covered in this particular week. They are as follow. So we discussed the reciprocal lattice, where we discussed the concept of the G star H care. How do we find the G star H care? And we also discussed that how G star H care is related with the DH care. That is the interplanar spacing in the real space. So this is a relation between the real space and the reciprocal space. Okay, and using this and the metric tensor, which we discussed just after it, we can find the length of the G star H scale. Right. After that, we discuss the property of the metric tensor in the real and the reciprocal space in both the cases, and in what case we should use the real and in what case we should use the reciprocal space. We are going to discuss. There is one thing that reciprocal space is mostly used when we want to find the interplanar spacing between the HKL. Okay, so we will use the property of the metric tensor when we want to find the HKL interplanar spacing between them. Okay, this part has been discussed. Then how do we transform the direction in the plane? Okay, so we know that in the real for the real space, we when we are dealing with the real space, most of the time the directions are the one while solving the question. Directions are the one which is mostly deal in the real. But for the planes, we need to go in the reciprocal space to find the length, to find the angle between them. Because in the reciprocal space, we know the planes are treated as a point. That is, the plane are treated as a vector of single point. When we can convert a plane in the real space to the point in the reciprocal space. So this is real and this is reciprocal. Usually we denote by the star. Okay, and this is how we do the transformation of the direction in the plane. We can transform the plane from a one Miller indices, from the one basis vector to the another basis vector. Okay, we have also computed the volume of the crystallographic unit cells. Okay, and finally, the orthographic projection of the crystals is started. Okay, so we are going to solve the questions based on all these things. Two things I would like to tell you that in this particular session, pardon, there was some network issue. I think now, pardon, there was some network issue. I think now it's good. Yeah. So yeah. So in this particular sessions, we are going to discuss the not only the questions. If you have any doubt regarding the concept that has been discussed with the Rajesh Prasad sir, okay. So you can also discuss with me those things and get it clarified. Along with that, if you are facing any difficulty in the assignments of the previous weeks, let us say, those also you can discuss with me. Let you solve the question, but you are not able to get the answer. The scores is already been updated on the website for the week 1 and week 2. If you're not able to get those things, or if you want to discuss something in regard to that, you can also discuss those things with me. Okay, so let's get to the first question. Yeah. So the question is telling us. Let us read it first. What is the interplanar spacing of the real plane R? So how the interplanar spacing for the real plane, that is they are asking about the DHKL, how it is related. proportional to the modulus of the corresponding reciprocal lattice vector. Reciprocal lattice vector, that is a H A star K B star and L C star. Okay, so this is the and their modulus. So it is they are telling that a real lattice plane is proportional to their interplanar spacing is proportional to the this. This is the first option, and the second option is telling that it is proportional to the real lattice vector, that is HA plus KB plus LC. HK and all they are Miller indices of the plane. This is the first option, this is the second option, and the third option is telling that they are inversely proportional to the real lattice vector, the modulus of the real lattice vector, that is HA plus KB plus L times C. So this is option C, and the last option is telling that they are inversely proportional to the modulus of the corresponding reciprocal lattice vector, the modulus of the reciprocal lattice vector, HA star, KB star, and L C star, and this is nothing but the option. So it's very easy to answer these questions, right? So here we can see that DHKL, the DHKL will be inversely proportional. We already discussed that the DHKL, D of HKL in the real space is inversely proportional to the modulus of the G star HKL, their modulus, and which is nothing but the option D. So option D, the question 1 is correct. Okay, and that's how we have solved the question number 1. If you have any doubt, please let me know in the comment box. Meanwhile, let's move to the question number 2. Or also you can unmute yourself to discuss with me. Let's discuss the question number 2. The question number 2 is telling that a vector in the reciprocal space is perpendicular to the corresponding plane in the real space, perpendicular to the corresponding plane in the reciprocal space, perpendicular to the corresponding vector in the real space, perpendicular to the corresponding vector in the reciprocal space. Okay, so this is what in the lecture there are the two properties of the G star is discussed, G star HK. One which we used in the last question, that is the G star HKL is 1 upon D of HKL, its modulus. The another thing which we discussed, the another thing that professor has discussed with us, that HKL is equals to the HKL is perpendicular to the G star HKL is perpendicular to the real plane HKL. Okay, and so we can say it will be perpendicular to the corresponding plane in the real space. In the reciprocal space, if there is a vector, this is a vector in the reciprocal space HKL, and it is perpendicular to the real space HKL plane. So the option A is correct option. Okay, both the questions were very easy, and both of them just based on the properties of the G star HKL. Okay, yeah. So let's move to the question number 3. Yeah. So in the question number 3, we can see what it is asking. Let us read it first. In a cubic crystal with a lattice parameter A, so a parameter is given, lattice parameter A is given. An oxygen atom is placed at the position OO. Okay, let us say this is the origin and the oxygen atom is there, OO. This atom is bonded to the titanium atom. The location at the position half O and half O half. Okay, so there are the two titanium atoms are attached. Okay, so let me mark them with the red. So this is a one titanium atom, and let us say this is another titanium atom, and their locations are half O, half, and half O. Okay, so these are the location of the titanium atom that is been there. And what we need to find the angle between these two bonds. This is something which is missing. Let us say this is theta and theta is something which we need to find. Okay, see, this here it is mentioned that it is cubic in nature, so it's a cubic crystal. It is very easy to solve this question just by the simple geometry, but our objective is not to solve it by the just by the geometry. We want to understand the concept. We want to apply those concepts that has been discussed in the class, so that we can also apply those things in the more complicated system. For example, the triclinic, monoclinic, and all. Okay, so we will try to focus on the concept that is need to be used over here. How to find an angle between the two vectors? We need to find the angle between them. Let us say I have a vector A and I have a vector B, and I have to find the angle between them. That is nothing but we can do the cross product of them, and we will get mod of A, mod of B, cos of theta. From here I can find the cos theta will be equal to the A dot B divided by mod of A and mod of B. If it has been the Cartesian coordinate system, for our case it is Cartesian, but still we will solve in such a manner that even if it is not the Cartesian, even if it is not the orthonormal system, we should be able to solve it. So we know when we are doing the dot product in the crystal coordinate system. Okay, so in that case, if we want to find the dot product between the A and B, let us say A is having the Miller indices of A is having the Miller indices of 1 half half O, and B is having the Miller indices of half O half. So in between them there is a one tensor, one matrix will come, that is a metric tensor. And we know how we can find the metric tensor for the cubic systems. Okay, let us try to find this metric tensor. So we'll try to find A dot B. From this we'll try to find the magnitude of A, and we'll also find the magnitude of B. Okay, so let's do it. So we are having the G. We want to find the metric tensor. Metric tensor is nothing but A dot A, A dot B, A dot C, B dot A, B dot B, and B dot C, C dot A, C dot B, and C dot C. A, B, C are the basis vector. Okay, in our case it is A, and A, and since they are cubic, so they will be 90° with each other. Okay, so let us say this is A, this is a B, and this is C, but all of them magnitude wise they are equal, and the direction they are orthonormal with each other. So the dot product between the AB and AC, they will be 0, and BA and BC also will be 0, CA and CB will be 0. So we can write this as A into A, that is a square. This will be nothing but 0, 0, 0. B into B, again it will be A square. It should be B square, but they are equal with each other, so we can write A square. 0, 0, 0, and it will be again A square. Okay. Okay, since we just need to find the lattice parameter is given to us A, we just need to find the angle between them. See, lattice parameter is given, but we need to find the angle. So we can treat A for a time being, we can treat them as a 1, 1, 1, 1. Angle is not going to affect by the magnitude of the basis vector. So this is how we find the G. So we can find A dot B as A is half O, and the metric tensor we got to know 1 O O O 1 O O O 1, and we can say here that it will be half O half. We just need to do multiplication, simple multiplication. Let us multiply this particular row with this particular column. What we will get, half O, we will get is as this will be half only, the remaining term will be 0, and here all the term will be 0, here it will be half again, so this is half 0. Simple multiplication again, half multiplied by half, that is 1 by 4, this will be 0, and again this will be 0. So we got the A dot B to be the 1 by 4. Okay, so the upper part is clear. That's how we can find the A dot B. Now we need to find the magnitude of A and the magnitude of B. Okay, and it is also very easy to find magnitude of A. That is, we need to find this magnitude and this magnitude. Again, for the this particular case of the cubic crystal, it is very easy. We can, since it is a Cartesian coordinate system, it will follow. We can find it, but still we will restrict ourselves that ourselves to the Cartesian coordinate system. Sorry, crystallographic coordinate system, so that we can solve all the types of question even if it is not the cubic. So let us try. Let us see how we can find the magnitude of A. What is the process to find the magnitude of A? Okay, so we can say it will be the root of dot product of A with A. Okay, their mod. We can say it like that. Okay, and we know how we do dot product. For dot product in the crystallographic coordinate system, we need the G, metric tensor in between them. So again, we know what is A. Here we can say half O, that is half O, and G we know 1 1 1 O O O O, and remaining part we know half again half O. First we will write in the row, and the second we will write in the column. Okay, so just let's try to multiply them also. What we will get in the first time, it will be, let's multiply this with this. So half O, and here we will get half. Here we will get half again, and here we will get 0. If we again multiply them, what we will get 1 by 2, sorry 1 by 4 plus 1 by 4, which is 1 by 2. This is how we solve for the A. And similar manner we can find for the B also, and if you repeat the same things again for the B, we will get for the modulus of B will be 1 by 2. Okay, and that's how we got all the stuff that we needed, A, B and A dot B. We can substitute them. So cos of theta, it will be equal to the cos of theta will be equal with the 1 by 4 divided by 1 by 2 times 1 by 2. That is 1. Did I made any mistake? Let's have a look. Yeah, I not took the mod. Sorry, I not took the root. So I have to take root of all of them. So it will be root of 1 by 2. And again here it will be root. So it will be root 2 and root 2. Okay, then they will multiply. It will be 1 by 2. And the answer which we will get is 1 by 2 only. So theta here in this case, that is, it will be 60. Okay, so I hope this is clear. Please let me know if there is any doubt in this. You can let me know in the comment box. And meanwhile, if there is no any doubt, we can go to the next question. Please have a look once. So what we did entirely is, we know how we can find these things. Okay, so we find A, we find B. In order to find the dot product, in order to find the angle between them, we need to find the dot product, and we need to find the magnitude in between them, magnitude of A and B. For that, we use the metric tensor. Okay, I wrote it wrong. It should be half 0 half. Like one should be in the row and another should be in the column. Then we went to find the magnitude. How to find the magnitude? A, G and A. That is the metric tensor we are using again. Half O and so on and so forth. We multiplied them. We got these things, and again multiplication only. It result in these things. Simple calculation. The theta value we will get, and that's how we have solved this particular questions. Okay, so let's move to the next question since there is no doubt.
question number 4. Okay, so what it is telling that consider a monoclinic crystal with a lattice parameter A, B, C as given to us, and beta is 120. What is the angle between 101 and 201? We need to find the angle between them. We just found the angle between the two vectors, but that was in the crystal coordinate system. Sorry, that was for the case of the cubic system. Now we are in the little bit evolved system, that is a monoclinic one. Little bit complicated, not so very complicated. We can solve it. So the process of this solving this particular question is exactly same what we repeated in the previous one. Let's do it. So we need to find the angle between 101 and 201. The box has been used, it means that they are the directions. They are not the plane, they are directions. Okay, so let's do that. So first of all, what we will do, we'll find the metric tensor, which is a dot a dot b, a dot c, b dot a, b dot b, and b dot c, c dot a, c dot b, and c dot c. You guys can also solve with me, okay, on your end. So what we can say here is that let us for the monoclinic system, let us write the for the dot product what we will get, that is the angle between them we need to find, right? So for the monoclinic, what we know, alpha is equal to the beta is equal to the 90 degree, and gamma is equal to the 120 degree, right? So for them we can write it. So a dot a will be ab cos theta. Sorry, a dot a will be a square. A dot b will be ab, angle between them. What is the angle between a and b? Angle between a and b is gamma, that is cos of 120. Cos 120 is minus of 1 by 2. A and c, what is the angle between a and c? A and c dot product will be 0, since the angle between them, that is a beta, is 90. So this will be 0. Right? Then b dot a, what we can say is it will be minus of a by a b. Same, it will be since dot products are commutative, so both will be equal with each other. Okay, and then again b dot b will be b square. B dot c will be equal to, again what we can say, b and c, that is the angle between the b and c will be alpha, which is 90. Again it will be 0. Okay, in a similar manner we can find this will be c square, c dot b will be again 0, and this will again be 0. And that's how we find the metric tensor. So we can write them as a square minus of a square by 2. Since a and b both are same, in the monoclinic a is equal to the b, but it is not equal to the c. Right? So a and b are equal with each other. 0 minus of a square by 2, and this will be a square, this will be 0, this will be 0, 0, and this will be c square. Okay, and that's how we have found it. We found the value of g, metric tensor. But let's move ahead and let us see what we need to find. Actually, what we needed to find, we need to find the angle between the 101 direction with a 2 bar 01. So in order for us to find this in the crystal coordinate system, we will write them as 101 times metric tensor times 2 bar 01. Okay, this we write in the row, this we write in the column. We are following the conventions. Okay, so let's write them. So what we have got over here, Here it is a square minus of a square by 2, o, so on and so forth. We can write them as it is. This will be a square minus of a square by 2. This will be 0 minus of a square by 2. A square 0 o c square. And this is how it is. Simple mathematics. In this way you can find the what is the dot product between the, you will get the value of this. In the denominator, what we need to find, this is a cos theta, it will be equal to this divided by magnitude of 101 directions. Okay, so these directions, magnitude of this we need to find, and also the magnitude of 2 bar 01. This is what we need to find. So how it can be done? 101, which we will find over here, times 2 bar 01, the whole divided by root over 101 dot product of with the 101 only. We will get the magnitude and we'll take that particular magnitude as it is, times root over 2 bar 01 times dot product of 2 bar 01. So in order for us to complete this dot product, we will use this particular metric tensor which we just found out. Okay, so in the similar manner, one can find the numerator and the two parts of the denominator in the similar manner going. You will cut the things in the numerator and denominator, all the variable term will be cancelled out with each other and you will get the value of cos theta. Since it will be quite lengthy and it's not that very evolved calculation, we can skip this, and the purpose of this particular question is to know that how one can solve these types of questions. Okay, so from now onwards, if we face that we want to find the angle between the two things, two directions, even if it is not the Cartesian coordinate system, still we can do that, whether it's triclinic, monoclinic, orthogonal, or rhombohedral. Any case, we can find it. All we need to find, the most important thing in all this case, is the metric tensor, that is a G. Okay, so I hope this is clear. Please let me know in the comment box if you have any doubt, or else in meanwhile we can proceed to the next question. Or you can also unmute yourself if you want to discuss some things. Let's move to the question number 5. Okay, so what question number 5 is asking us? Question number 5 is asking that we need to find the expression. We need to, okay, just a minute guys.
No.
Yeah.
So every time we have to write the same equation for metric tensor. Actually, I'm little bit late, so I didn't get it.
See, metric tensor is associated with the unit cell, or we can say the metric tensor is associated with the basis vector. So as long as you are
Yeah.
restricting yourself with the same basis vector, that is, let us say someone is restricting themselves with the basis vector A, B, and C.
Yes.
They want to use this particular basis vector. We use in the Cartesian coordinate system, we use Ex, Ey, and Ez. These are the basis vector which we use. So once you fix your basis vector, your metric tensor value is already got fixed. That is 1, 1, 1, and remaining thing will be 0, 0, 0, and 0. Pardon, let me fix my camera. Yeah, I think now it's
No,
fixed.
it's clear.
Yeah, okay. So once you are fixing your coordinates, your basics system. So for the crystallographic for the Cartesian coordinate system, 1, 1, 1, and remaining thing will be 0. This is the metric tensor that has been fixed already.
Yes.
If you are using anything else, that is A, B, and C, and their magnitude is fixed, their angle between them is fixed now. As long as you are using the same basis vector, your metric tensor is not going to change. Okay.
So you don't need to find a metric tensor always. Once you have found for the given basis vector, you can use this multiple times. So just like what we were doing in this particular questions, let us say question number 4, what we were doing over here, we just found the metric tensor for this, right? For this two thing, but the metric tensor for the remaining part also we will use the same. It's not gonna change because the basis vector remain as it is. That is it is corresponding to the monoclinic system. Okay, I hope it is clear. Please let me know.
Okay, thank you so much. Yeah.
Yeah. So let's move to the next question, question number 5. So question number 5 is asking us we need to find the length of the vector UVW in a triclinic crystal system. We know how evolved it is, triclinic crystal system. Okay, so there is a direction is given to us UVW, its Miller indices is given, and we need to find the length of this particular basis, this particular direction, this particular Miller indices. That too in the triclinic system. We know in the triclinic A is not equal to B. It is also not equal to the C, and the angle between them, that is
See.
between A and B, it is gamma. B and C, it is alpha, and A and B, A and C, it is beta. So all the angles, they are not equal with each other, and they are not equal to the 90 degree. Okay, so how do we solve these things? We need to find the length of the vector UVW. We know how we can find the length of a particular vector. Let us say A is a vector. We just found out how we can find the length of the vector. A dot A. We'll take the magnitude of it and take a square root. Okay, so that this is how we will find the so in order for us to perform this particular thing, A vector dot A vector, we need to find, for the dot product need to do, we need to find the metric tensor, that is G. Let us try to do it. So the first term in the metric tensor A dot A will be nothing but A square only. It's not going to change. Second term is A dot B. We know dot product of AB, that is AB, and the angle between them. Angle between A and B is cos of gamma. Next term will be A and C. AC, and the angle between A and C is nothing but beta. So cos of beta. Right. Next term, let's go to the next term. Here it will be again, it will be BA. This will be same as AB cos gamma. So AB cos of gamma. Here it will be B square. Here it will be angle between this is the B and C. Here it will be B dot C, right? So better I write instead of getting confused. Let us write them. AA, AB, AC, BA, BB, BC, CA, CB, and CC. Okay. So here it will be B and C. That is a B, B, C. Cos of angle between them, cos of angle between B and C, that is alpha. And that's how we can complete all the things. That is AB cos of beta and BC cos of alpha, and it will be C square. We found the metric tensor. That's all we needed to do that. Okay, so this is a metric tensor corresponding to the triclinic crystal system. So let's move ahead and do for the particular, let's complete our question. Let's complete our answers. Okay, so let's try to go on the next page. So we need to find the magnitude. We need to find the dot product between A and A. And we know the A is U, V, and W. And here it is metric tensor. U, V, and W. Okay, we will write our our metric tensor over here. It will be A square
I'm writing the same thing which I wrote in the last paper. Cos of gamma, AC cos of beta. Here it will be AB cos of gamma, B square, BC cos of alpha, AB cos of, it got hotspot, okay, BC cos of alpha and C square. I hope it is clear. It's not that well written, but I hope it will do. Then UVW. All we need to do is simple matrix multiplication. Multiply first row with this particular column. What we will get? We will get U times A square, U times AB cos of gamma plus W times, it will be V, sorry, it will be V, and W times AC cos of beta. Similar manner, we will multiply all of them. We will get second term. This is the first term of the matrix. Similar manner, we will get the second term, that is V times AB cos of gamma. Sorry, not V times, it will be U times, and V times B square plus of W times BC cos of alpha. And the third will be U times AB cos of beta. How I wrote this? AB cos of beta. It will be AC. Instead of AB, it should be AC. This is AC, pardon. So here also it will be AC. Okay. AB cos of beta plus AC cos of beta plus V times BC cos of alpha plus W times C square. Now, these are the three entity of the matrix. These are the another three entity of the matrix. We need to multiply them. Okay, and once we multiply, we will get the entire our equation. U times, we just have to multiply this row with this column. Okay, so U times entire thing, V times this second entire, and W times this. So we will write the U. We will get U square A square plus U times V, U times V AB cos of gamma plus U times W AC cos of beta. That is, U is multiplied with this entire thing. First one, first entity. Again will be, the second will be V will multiply with this entity. So UV AB cos of gamma plus V square B square plus U, sorry, V W BC cos of alpha, and W we will get, W will multiply with the entire term, this third term, that is a UW AC cos of beta plus VW BC cos of alpha plus W square C square. This is the entire thing which we are getting, and we can just this is the formula which we are looking for. We can just arrange few terms. We can make these terms together, and cos of alpha terms we can make them together. Okay, and cos of beta terms we can make them together, and cos of gamma terms we can make them together, and just rearrangement, and it will result in the final formula. Okay, and that is how we have now we are in the state where we can find the length of the any vector, length of the any basis vector, length of the any direction in the given basis vector, and even in the most complicated basis system of a triclinic crystal system. Okay, so remaining thing will be very easy for us also. Like in the monoclinic system we will go, it will be more symmetrical and the less calculation, the formula will be less we got. So on and so forth, one can find the length of a particular vector UVW defined by UVW indices in 7 crystal system, in all the 7 crystal system. Okay, and that's how one can do it. So this was the question number 5. Please let me know if any doubt, or you can also unmute yourself to discuss if you have any doubt in this particular question that we have solved. Okay, since there is no doubt, let's move to the next question, question number 6. Okay, screen is not that clear. Let me focus it. Yeah, this will do. So here we can say what we need to do. We have to compute for a crystal with a lattice parameter this. This is a lattice parameter is given. The distance between the 1 plane. Till now, we were dealing with the directions. Okay, but now we are going to the plane part. It will be little difficult, but not that much. Just on a few things will be changed. So let us see which is this particular system is given to us. That is a okay. Yeah, the given system is A is not equal to B is not equal to C. That is 3, 4, and 6. Alpha they are telling it is 90 degree, and beta is telling that it is also 90 degree. It is they are equal with each other, and C is equal to the 120. So just a minute, guys. So what we can see over here is that the angle look like the hexagonal, but the A and B are not equal with each other, and so this even not belong to the hexagonal. This is a triclinic system. Okay, and we know that we just found the crystallographic direction. Sorry, metric tensor for the triclinic system, and we deal with the directions. But now the thing is that we need to deal with the planes. We know that in the real space, the plane is it will cover the entire spaces. It is a plane. It will look like a plane. Plane is a plane only. But when we go to the reciprocal space, the plane which was in the real space, it will become to the direction. That is point. And so all the thing that we discussed in the real space, we can do in the reciprocal space. That is finding the G matrix and that is the metric tensor and the way we found the direction between them. Okay, so we need to find the distance between the 1 plane, and we know how we find the distance between the 1 if it has been the real. For the real, let us say this is for the direction 1 how we 1 how we can do that. That is 1 we will take the dot product with the 1 in the Cartesian in the crystal coordinate system, and here we will use the metric tensor. If we want to do same things in the reciprocal space, instead of this G, we will need the reciprocal metric tensor. So now the question which was asked by you, now the G has been changing, the metric tensor has been changing because we change our basis. In real space, our basis was A, B, and C. In the reciprocal space, our bases are A star, B star, and C star. This is our reciprocal basis. Since we are changing our reciprocal basis, our metric tensor will also be changed. As discussed by the professors, Professor Rajesh Prasad, what we can say that there is a relation between the reciprocal metric tensor and the real metric tensor, and they are reciprocal of each other. This is just a definition of the reciprocal itself also, right? Anything in the real space is just a reciprocal, reciprocate it and you will get in the reciprocal space. And so if we know that the G in the real space, if you know the matrix in the real space, you can very easily find the metric. Just you have to inverse of the matrix. We know how to find the inverse of the matrix. Okay, simple mathematics, class 11, class 12, and we can do it. Okay, so now our question is reduced to find the first we will find G of the real space, then we will find it inverse and we will get the G star. And now we can find the distance between the 1 1 1 plane. Okay, so we need to find the distance between the 1 1 1 plane, but if we go to the reciprocal space, it will be the direction. So now we will follow the same procedure, that is this thing, and for this only we need G star. So let's try to find the G star first. For that we will find the G first. Same thing, A dot B, A dot C. In the assignments you will find the few questions are like in this particular way only. B dot A, B dot B, and B dot C. C dot A, C dot B, C dot C. Here what we will do, we know the value of A, B and C. That is, let me write it somewhere. A is equal to the 3, B is equal to the 4 and C is equal to the 6. Alpha we know, alpha is equal to the 90 and also beta, and gamma is 120 degree. Let's try to apply them. Dot product between A and A, it will be A square that is 3 square, that is 9 we will get. A dot B, 4 3 is 12, but what is the angle between them? Angle between them A and B, that is the gamma is 120 degree. So here 4 3 is 12 and the angle between them is 120, that is minus of 1 by 2. Cos of 120 is minus of 1 by 2. We will get minus 6 over here. A and C, the angle between A and C will be beta, and beta is 90 degrees, so we don't need to worry about this, it will be 0. And B and A, let's talk about the B and A. Again the A and B will be same as the B and B, dot products are commutative, so it will be minus of 12 by 2, that is minus of 6. B dot B, that is a 4, what we will get? 4 square, that is 16. And B dot C, we will get, what is the angle between B and C? B and C will be alpha, and alpha is 90 degree, so this will be 0. And so this will be 0, this is also 0, and C square we know that is a 36. And so we can say that our metric tensor is 9, minus of 6, 0, minus of 6, 16, 0, O, O, and 36. So this is the G, but we need to find the G star. A simple calculation we need to do. I will use the calc to do that. Okay, so let's feed our entire thing over here. So what we can say, A is 9, then minus of 6, then we will get 0, and then there is minus of 6, then there is a 16, again 0, then 0, 0, and 36. This is, we have filled our matrix. Just let me cross check it. 9 minus x 0 minus 6 16 0 0 36. Perfect. So we will go to the matrix, we will select 3 and we will take the inverse of it. Let's see what we are getting. Oh, we are getting very not so good value, but still it's okay. So we can write G star as the value which we are getting 0.1481, and we are getting 0.0555 and 0, 0. Here we are getting again 0.0. See, this reciprocal metric tensor itself is symmetrical. Along the diagonal, we can see they are symmetrical. And that's how we have found the value of G star. We got the value of G star. Again, the process will remain as it is, right? So what we will do, we need to find this particular length of the 1 1 1. Interplanar spacing, now it will in the reciprocal space, it is the length of the vector
1 1 1. Here we will write the G star, and here we will write 1 1 and 1. Very easy. Just simple mathematical calculations will be there, and we can solve it very easily. Okay. I don't think there is any difficulty will be further in to solve this type of questions anymore. Okay, and I leave it to you to solve this further. This is very easy right now. Since we find the G star over here, it can be solved. Okay, so now what we can say that we can find the interplanar spacing, the distance between the 1 plane. In the cubic crystal system, what we know that the interplanar spacing, that is a D, is given by A divided by root over h square plus k square plus l square. But from the procedure that we have followed, what we can do now, we can find the interplanar spacing in any of the system. If we follow the same procedure we followed for the triclinic only, the most evolved one. If you follow the same procedure, you can find the interplanar spacing for the any of the Miller indices in any of the crystal systems. Okay, let's move to the next question. Question number 7. So here is the question number 7. Okay, what question number 7 is telling us? Let A, B, and C define the conventional basis in the crystallographic coordinate system. Okay, so it is defined in the conventional basis. Okay, let A, B, and C is the conventional basis. A new set of basis vector are defined in terms this vector as follows. So they are defining the new set of basis vector, that is A dash, B dash, and C dash. Okay, so this was the basis vector 1, this is the basis vector 2. That is, we are transform one basis to the another basis vector. Okay, so what we need to do, we need to find Miller indices of the direction. Okay, so we need to find the Miller indices of the direction this in the new basis vector. We also need to find the Miller indices of the plane this. We need to find the Miller indices of the plane in the new basis vector. Okay, this is what we need to do. Let's focus on the first question first. Okay, that is, we need to find the Miller indices of the direction 1 O 1 bar in the new basis. It's not that very complicated. We know how we can do that. In the lecture, it has been taught that for this, we need to know the general coordinate transformation matrix. That is a Q. What Q will do? Q will transform A, B, and C, which is our initial basis vector. Q is a matrix. Q is a matrix in such a way that it will transform A, B, and C. It will transform the basis vector A, B, and C to the A dash, B dash, and C dash. So now, once we form this particular, once we get what is this Q is, we will easily be able to solve this particular question. Let's first find the Q, and we will proceed further that how we can solve the questions. Okay, let's take the other one. So we need to find A in terms of A dash, B dash, and C dash. What is given over here? A dash is given, that is 2A plus B plus C, and C is given C dash by 2. Let's put all the things over here. So we know that C is equal to the C dash over 2 from this. So from the above equation, that is this one, what we can say that B will be B dash minus of C. So B dash minus of C, C is C dash over 2. We find the B and C, we can find the A also. A will be equal to the A dash by 2, A dash minus of B minus of C, the whole divided by 2. Right, we can write them as A dash
minus of b. We know what is a b. This is a dash by 2 minus of b by 2 and minus of c by 2. Let's find all of them. Better I use the another one. So what we can do over here is that this is a will be equal to the a dash over 2 minus of b over 2 minus of c over 2. A dash over 2 minus of, how we can write b? We can write that b dash minus of c dash over 2, half of the entire thing, half of this entire thing. So here it will be 2 and here will be also be 1, 2 will come. Minus of c by 2. C by 2 is nothing but c dash by 2. So that is the, sorry, c is c dash by 2. So c by 2 will be c dash by 4. Let's find them. A dash over 2 minus of b dash over 2. This will be plus of c dash over 4 and minus of c dash over 4. It got cancelled, right? Oh, I should have not done it. So what we can say, a dash over 2 minus of b dash over 2. So we got the value of a. Unnecessary I did entire thing. We know that b plus c is b dash, so we can write, instead of this we can write b dash. So a dash will be equal to the 2a plus b dash, and so we can write the a will be equal to the a dash over 2 minus of b dash over 2 from here only, but still it's okay. So that's how we have got the value of a, and we have got the value of b in terms of b dash minus of c dash over 2, and we got the value of c, it is the c dash over 2. What we need to find? We need to find the general coordinate transformation matrix which will transform a, b and c to a dash, b dash and c dash. In the assignments you will find question like this. Okay, there are in fact two questions like this. So what we can say, a in terms of a dash, so the value is associated with the a and a dash is 1 by 2, so we can write a 1 by 2 over here. A and b dash is minus of 1 by 2. A and c there is no, that is 0 of c dash, we can say that it will be 0. Let's go with the b. B is, there is no a term, so b is associated with the a dash will be 0. B with b dash will be 1 and b with c dash will be minus of 1 by 2. For the c we know that remaining terms are 0 and the only term is 1 by 2. So this is what we have got the q. So we got the general coordinate transformation matrix, and now using this, let's get back to our question. We need to find the direct Miller indices of the direction 1, O, 1 bar in the new basis. Okay, this is with respect to A, B and C. We need to find with respect to the new basis. So in order for us to do that, the Miller, what we can say, the Miller indices in the new basis, let us say it will be x dash, y dash and z dash. I'm taking anything, okay. Okay, and over here we can say that whatever we found the q matrix will come over here, and the initial, which was nothing but the initial direction 1, O, 1 bar. Pardon me. So here we can write the value of the q matrix, and q is, I'm just writing that particular thing, half O half minus of half 1 O minus of half and half. All we need to do, we just need to multiply them, simple matrix multiplication, and we will get the value. Let's multiply that. X dash, y dash and z dash, we will get, this is a Miller indices in the new basis vector. Multiply them. 1 by 2 multiply with 1 by 2, remaining term will be 0 because it is 0. So we will get 0.5, 1 by 2. Let's multiply this with this particular terms. Minus of 1 by 2 with 1, minus of 1 by 2. This will be 0, this will be 0. So minus of 0.5. Let's multiply these things. This is 0, and half, it will be minus of 0.5. So the Miller indices of 1, 1 bar in the basis vector A, B and C is 1, 1 bar. I should write the direction, not like this in the box. But in the case of A dash, B dash and C dash, what we are getting? It is 1 by 2, minus of 1 by 2 and minus of 1 by 2. And that's how we got the new basis vector. Sorry, Miller indices in the new basis vector A dash, B dash and C dash. The magic was done by the Q. So how you can find the Q? You just need to know how your old A, B and C are related as with the A dash, B dash and C dash. How they are related with them. Once you know how they are related with each other, you can easily find the answers. You got the Q, and that's it. For this particular relation, how to know that? Either it will be directly given in the question. See, in this particular question, it was you might think that A dash, B dash, and C dash are given directly. Which we are not using it. We are only using the A, B, and C. We are finding the A, B, and C in terms of A dash, B dash, C dash, not A dash, B dash, C dash in terms of A, B, and C. It's a reverse way, and so we are able to solve this particular question in this particular way. Again, this was done for the direction 101 bar. What about the plane 101 bar? Now we need to find for the plane also. Again, we will use the same logic that for the plane we can go to the reciprocal lattice where the entire plane will be treated as a point, a lattice. Okay, in the reciprocal lattice, the lattice is made up of the planes. Each point is belonging to the plane. So the way we are treating direction in the real space, we will treat the plane in the reciprocal space in the same manner. So the entire process of this which we followed will remain same. But for the real space it was Q. Okay, but for the reciprocal space it will be Q star. We also need to know the transformation matrix, right? Which will transform, which will do the magic for us to convert a particular mirror indices from one basis to the another basis. Okay, so how do we find this Q star? Just like the metric tensor, the Q star in reciprocal space is also the inverse of the real. Okay, so in order to find this Q star, we will find the inverse of the Q. Let's write the Q again. So the Q was 1 by 2, that is 0.500 minus of 0.510 minus of 0.5. In order for us, instead of this Q, if we want to find the Q star, what we need to do? We need to take the inverse of this. Pardon for that particular call. Okay. So here, what we can do is Q star we need to find. Okay. So we need to find the inverse of this. Let's find the inverse of this. It's very easy. Again, we'll use the calci. One can use the simple mathematics also. I will go with the calculator.
So here we will write the entire thing 0.5, 0 and 0, minus of 0.5, 1 and 0, then 0, 0.5, no, it is minus of 0.5 and then it is 0.5. That's how all our Q matrix is 0.5, 0, 0, 0.5 minus 1, 0, 0, 0.5 negative and 0.5. Okay, let's find the inverse of it. And this is the inverse. We are getting the 2, O, O. This time we are getting easy terms. And that's how you find the Q star. Okay, so now we need to find the Miller indices of 1, O, 1 bar, this particular plane, which has been treated as a direction or lattice point in the reciprocal space. The only difference, the way we treat the Q and Q star, the way which we write is that now instead of writing as a column vector where we are writing over here, let me show you. Yeah, here. While transforming, we were writing them as a column vector in the real space. But when we will do the same thing in the reciprocal space, we have to write them in the row 1, O, 1 bar. Okay, it will be multiplied with the our Q matrix 2, O, O, 1, 1, O, 1, 1, 2, and we will get the our. Let us write the. I will write H dash, K dash, L dash. Okay, so now we can just do the simple multiplication. This will multiply with the simple multiplication will do. It will give us 2 and remaining term will be 2. This will be 0 and minus of 1. 2 of 2 and minus of 1. Next term will be multiplication of these two things. This will be 0, this will be 0 and this will be minus of 1. Okay, and for the third one this will be 0, this is 0 already and this will be minus of 2. So what we are getting over here is 1, minus of 1 and minus of 2. So that is the 1, 1 bar and 2 bar. This is the Miller indices in the A dash, B dash and C dash system, which was 101 bar in the ABC system. And that's how we have transformed this entire thing. Okay, so if you have any doubt, please let me know, or else we can move to the next questions. Let's recap the entire process first once. Okay, so we were needed to find the directions. We need to find the Miller indices of a directions and a plane when we are transforming from basis vector b1 to b2. For the direction, we are in the real space and we are using the magic vector, that is a general transformation matrix, general coordinate transformation matrix is a Q. But for the plane, when we were dealing with the plane, we were transforming it to we were using the Q star. So now we are in the position where we can find the Miller indices of any plane when we are transforming from one basis to the another basis, where this basis transformation is useful to us. Okay, this is one question which one should ask, that where this particular basis transformation is useful. Let's consider that FCC is having the 4 lattice point associated with it. Okay, face centered cubic close back, it is having the 4 lattice point associated with them. But sometime we need to deal in the primitive, that is it should associate only one lattice point.
in the previous live session, we have discussed that how primitive the conventional unit cell is transformed to the reciprocal, sorry, transformed to the primitive one. Okay, and there how, and that's how this is the one, this here it basis will be A, B and C. Here it will be A dash, B dash and C dash, since we are going to the primitive basis. Okay, and this is where we need to use this entire thing. We need to use the entire, so one can find in this particular basis vector, one can find the Miller indices of the plane, Miller indices of the directions, which was associated with the ABC, that is the previous basis vector. Here, so two things which we discussed, that is a G star, Q and Q star, and their properties was that they are inverse of each other. Q and Q star are inverse of each other, and G and G star are the inverse of each other. Once you find the particular matrix, just inverse it, you will get in the reciprocal space. Okay. If there is any doubt, please let me know, or else we can move to the next question. Question number 8. Just a minute, guys. Not feeling well. Yeah, let's focus it. Okay, so now we are moving to the final concept that is being taught in the class. That is, we need to draw orthographic projection of a diamond crystal structure. Okay, orthographic projection of the diamond. Let's make the diamond structure first before discussing its orthographic projection. This scale. First, we will make a cube. We know how diamond cubic structure look like. Okay, so we know how we can write a diamond. That is a FCC lattice with a two atom motive, that is at 000 and 1 by 4, 1 by 4 and 1 by 4. So it has the motive of two atoms. So first is it will form the FCC. Okay, let's mark the FCC. Okay, all the corners have been covered. Now the faces. Top bottom face, parallel side faces, and the parallel front and the back face. This is how it is. Now there is also one lattice point. There is one more motive is associated, that is 1 by 4, 1 by 4 and 1 by 4. So from here it will be 1 by 4. From here it will be 1 by 4. Okay, we are following the particular direction. We will go over here. Let's say in front of this particular point, we'll go in the 1 by 4 direction. And here also so atoms are associated over onto this particular in front of these things. Okay, so there will be one more carbon atom over here, just in front of this also it will be there, and just in front of this also it will be there, and in front of this also it will be there. And that's how the diamond structure will look like. So if you see that is if this is 0 for a time being, let us say, yeah, then we can know the coordinates of the all the atoms. Let us try to find the orthographic projection of this from the top. Okay, on this particular plane. Okay, this is A, and let us say this is B, and we are falling on the A and B. We want to find the orthographic projection. This is different from the stereographic. Orthographic is very easy. You will find in the international table any space group number that has been presented in the international table will start with the orthographic projection only. So that is how we can do it. So first of all, this atom will project as it is. Let us say this is A, this is B. This atom project at this particular point itself. Same for this particular atom also, it will also project at this particular point. For these atoms, again the same procedure will be followed. One thing we should note that their amount is nothing but this is along the z-axis. For the z-axis we talk, it will be 0 only, and for this also it will be 1 only. So if it is 1 and 0, okay, if it has the corner of the cube, we don't need to mention that it's z coordinate. And x and y, we can already figure out what is the x coordinate of this. It will be in the a direction it is 1, in the b direction it is 1. In the c direction we are not going to specify, and since we are not going to specify, we mean that in the c direction it is associated with the each corner only, that it will be either 0 or it will be either 1. Same, let's go with the face centered, top one. So the top face centered will come somewhere over here, but will we write its coordinate? Will we write its z coordinate? No, again it will be nothing but 1. And for the bottom also, it will project at the same particular point, and bottom is at the z axis. If we talk about in the c direction, it will be at the 0. So 0 and 1. So we are not going to mention this also. Now let's talk about this particular parallel faces point. Okay, so now where they will project? They projected over here. Okay, this particular corner points was projected over here. This is in between them, so it will project somewhere over here. I'm marking with the different color, but for a timing, just it's for the sake of understanding. Somewhere over here it will be, just in between them. But its z coordinate is neither 0 nor 1. Its z coordinate is half. So we will specify over here that it is half. It is at the half. Same, let's try for the front and the back one. So for the front one, it will be projected over here. From the top, it will be projected somewhere over here onto this. So it will get somewhere over here. I will also make this black. Again, we know that this is nothing but 1 by 2 in the z-axis. So we will specify that it is 1 by 2. So for the any point you can find its coordinate. For this you can say that okay, in the a direction it is 1 by 2. In the b direction it is in the a direction it is 1. In the b direction it is 1. In the a direction it is 1 by 2. And the c direction it is again half. So what this particular point one can specify, because x and the y you are already getting from this diagram, and since for the z we are specifying it, we know the coordinate of the particular point. Okay, similarly we will go for the another lattice point. It will project over here another atom, and again it will project over here. Okay, and again we will specify that they are at the 1 by 2 and 1 by 2. I hope this is clear till now. So now, if you have any doubt till now what we have done, please let me know. Okay, since there is no, we can proceed. Just a minute, guys. Not feeling that. Yeah, pardon me. So what we can see for this particular from this particular point, we covered the all the FCC lattice point associated with the FCC. Now we are adding one more over 1 by 4, 1 by 4, and 1 by 4. Okay, we need to mark them. That is, we need to mark this one, we need to mark this one, and we need to mark this and this. Since they are at the V, they are something like V, like something over something. It will look like this. So along this, they are associated, and along this. So choose any of the diagonal like this, or face diagonal like this, and you will get the where it is associated. So from here, it is going 1 by 4 and 1 by 4, and again in the C direction, it is going at the 1 by 4. So from here, if I look, if I go by 1 by 4 over here onto this particular region, and then in the in the B direction, sorry, yeah, over here, if I go, I will get my point. But the point is neither 0 nor 1 because it is not lying on the top and the bottom faces. It is above by the amount of 1 by 4. Similarly, we can write for this particular point also, that is over here. In front of this particular point, it is at the 1 by 4, 1 by 4, and the 1 by 4. So let's from here we can go 1 by 4, 1 by 4. The point will lie somewhere over here. And in the z direction, it is at the distance of 1 by 4. So we have to specify it. So these two are over. What about the above one? So they are 1 by 4 associated with this 1 by 4, and associated with that in the C direction, in the downward direction, they are moving by the 1 by 4. Okay. So no, not with respect to this lattice point, sorry. They are associated with this particular lattice point. That is, it are going at the 1 by 4 over here, 1 by 4 over here, and 1 by 4 downward. So for this point, it is lying over here, 1 by 4, 1 by 4. I will come over here. So this particular point, it is. But in the C direction, it is going by the amount of 1 by 4 downward. So effectively, we can say from the base, it is coming by 3 by 4 amount in the upward direction. So we will write 3 by 4. Okay, and so the same will be for this particular point. Here it will be like, oh, it will be lie somewhere over here, and it will be again 3 by 4. And that's how we have drawn the orthographic projection of a diamond crystal structure. Okay, and it will look like this. Okay, so looking at this particular figure, one can make out the coordinate of each of the points. That is, coordinate of each of the carbon atom associated in the diamond cubic structure. Okay, so for the center, one will say either it will be half of 0 or half of 1, and that's how the question number 8 we have solved. If you have any doubt, please let me know in the comment section, or else in the meanwhile we can move to the next question. That is our final question, question number 9. So with that, we have solved the orthographic projection part also. So in the assignment, you will find few orthographic projections question. You can very easily solve it. The one which we did is a toughest one. It is one of the toughest one, I would say, not the toughest one. It was easy to visualize. In the room, one can try for the TiO2 system, TiO2 crystal structure, how its orthographic projection will look like. So now let's go to the question number 9. The question number 9 says that in 2004, NASA Mars rover spread examined the Columbia Hill region of the Mars and found the mineral goethite is known to form only in the presence of water. Okay, goethite will form only in the presence of water, and that's how they are discovering that okay, there was some evidence of the water on the Mars. So the goethite is orthorhombic. They are saying that it is orthorhombic. Okay, with 4 formula unit per unit cell. Okay, it is having the 4 formula unit. The value of A, B, and C lattice are given. So first of all, it is given that it is orthorhombic. Okay, so for the orthorhombic, we know A is not equal to B, which is also not equal to C. And we know the angle alpha is equal to the beta is equal to the gamma is equal to the 90 degree. A, B, and C are given to us, their values are given, and we can again verify that they are not equal with each other, and we can say that okay, yeah, we are in the orthorhombic system only. What we need to determine, we need to find the reciprocal metric tensor. Okay, reciprocal metric tensor, that is, if we are representing metric tensor by the G, it will be G star. We need to find the entire metric tensor for the orthorhombic ratios. It's not that tough. It's very easy, I would say. This is the first thing. The second thing, the general distance between the HKL plane. So they want us to find the HKL plane, the distance between the HKL, that is the interplanar spacing. Again, we are dealing with the plane. For the plane, we need to find the G star only, since we need to go in the reciprocal space. And so for that, it is also like if we are using for solving question number A, part A, we can easily solve question number B. The reciprocal metric tensor is specified for the geodite. Now we need to find the reciprocal metric tensor specific for the geodite. That is, we need to substitute all the value, that is A, B, and C, associated with the reciprocal, associated with the metric tensor, A, B, and C value. Once we find A now, we can just substitute all those value in the A, B, and C values, these values, and we will get the C part. Okay. Instead of going any further, first let's try to find the first part, the reciprocal metric tensor. Okay, let's use a different paper. They want us to find the G star. Reciprocal metric tensor. We can say it will be A star dot A star, A star dot B star, A star dot C star. Here it will be B star dot A star, B star dot B star, B star dot C star, C star dot A star, C star dot B star, and C star dot C star. Okay. And for the orthorhombic, we know. See, let's see. For orthogonal system, in the real space, if I'm right now I'm drawing for the real space A, B, and C. Okay, where A star will lie? A star will be nothing but a cross product of B and not B star. A star is a cross product of B and C divided by volume. So B and this is nothing but a scalar quantity, nothing to worry. B cross C will give us A star nothing but B cross C. So the A star is lying onto itself. The direction of A star is along the A only. It will be perpendicular to the B and C, right?
and we know this particular direction is perpendicular, that A direction is perpendicular to the B and C plane, and that is where A star will lie. In similar manner, since the way this is A star, the B star will lie onto this only. Their magnitude will be different, and it will be nothing but this will be C star. Okay. Divided by volume of the orthorhombic. What is the volume of the orthorhombic? It is A into B into C. It's just like the rectangle, multiply in one more direction, we will get the volume A, B and C. And we know the angle between B and C is 90 degree. Angle between B and C is 90 degree. So the cross product will be AB sin theta, sin 90, that is 1. That is a BC. It will be right at the BC divided by ABC. B and C will be cancelled and we will get 1 upon A. So A star is 1 upon A. And that's how we can write. And the A star into B star, that is the dot product between them. A star into B star, dot product between A star and B star. Dot product, since it is 90, it will be 0. So all the thing A star, B star, A star, C star, this entire thing will be 0, since they are orthogonal to each other. So only thing that will be left is A star dot A star. This will be 0, this will be 0, 0. B star dot B star, this will be 0, 0, 0. C star dot C star. A star dot A star will be nothing but A star square 0, 0, 0. B star square 0, 0, 0. C star square. And we know A star is 1 by A. So we can write it as A star is 1 upon A. This is 0, 0. 0, 1 upon B square. 0, 0, 0, 1 upon C square. And that's how we have found the metric tensor for the reciprocal space for the Goethite, sorry. Okay. So the part A is over, and that's how we have done it. Now, the next thing is that we need to find the general distance between HKL plane. General distance between the HKL plane, since it is plane, we need to go in the reciprocal space only, and we are in the reciprocal space. And we need to find the distance. Okay, we can do it in the reciprocal space. So for the HKL in the reciprocal space, we know, let's say we need to find the general distance, right? Okay, d of HKL. So we can write HKL G star metric tensor and then H, K and L in a similar manner. This is very simple. So what we can say, H, K and L. We just found the G star. G star was 1 upon A square O 1 upon B square O 1 upon C square. Again H, K and L over here. Simple multiplication, H, K and L. Let's multiply them. What we will get? This term will be H upon A square. Again will be K upon B square. And this again last term will be L upon C square. Again let's multiply them. This will be this H square divided by A square plus K into K is K square divided by B square plus it will be L square over C square. Okay, and that's how it is. We can find the interplanar spacing. Okay, in this manner one can find it. So that's how we have found the general distance between HKL.
Okay. See, one thing is that this is in the that is the HKL in the distance between them. It will be when one can say that this is in the reciprocal space. For the real space, if we want to distance, I also forget to tell this in the one of the previous question. We need to take a reciprocal of it. Okay, and that's how one can find it. Just take a reciprocal of this, and we are done with it. And also, yeah, last thing, since this is a dot product, we have to take the square root over all of them. So it will be 1 by 2. So we can write them as h square. Finally, the d-spacing of HKL plane is h square upon a square plus k square upon b square plus l square upon c square, the whole to the power of 1 by 2. Here, if a, b and c are equal to each other, that is in the for the cubic case, let us say, what we can say in that case, it will be 1 divided by root over h square plus k square plus l square divided by the whole divided by a square. It will be, we can take it common and we will write a, and the d spacing can be written as a divided by root over h square, k square and l square. Okay, if someone follows this entire same procedure, so not only for the orthorhombic or cubic or tetragonal, one can find for the even evolved system, that is triclinic one. Okay, and that's how we have solved the part B also. A and B part is over. Okay, so now the third one, we need to find the reciprocal metric tensor, that is the G star, where we have done it. We need to find this G star, which we find it over here, for the Gothite. That is, they are specifying is that solve for this only. That is, we need to put the value of A, B and C over here. Okay, we need to put the value of A, B and C. Okay, and just put one can put the values and they can find it. It is a C will be over. Now let's go with the D, the value of lattice spacing between the O to O to OO and 111 plane. Okay, that is C part. Sorry, that is D part. Lattice spacing. Okay, we need to find the lattice spacing between these planes. Very easy. We found for the general only, right? We found for the general that it will be 1 divided by root over h square over a square k square over b square plus l square over c square. And they are also specifying that this is for the Gothite. So we know the ABC value. We know the HKL value. We need to find the D spacing between them, lattice spacing between them. That is a D we need to find. So for all the cases, O to O to O 111, what we need to do, we need to find the, we will just substitute all the values over here and we can get the answer. So that's how we will find the D part. So now we need to find the last thing, that is the angle between the plane normals, this and this. We need to find the angle between the plane normal. Again, the same procedure we have to do. Okay, we need to do the same procedure and we can simply find it. We need to find between 101 and 1 bar 01 plane. This is the plane. In the reciprocal there will be direction and okay, it will be a point. It will be point in the reciprocal space, and in order for us to make a dot product in between them and divide by their magnitude, what we need for the magnitude, that is we need to find these things. Everything we need the G star, and G star we have already found over here. And so overall, the case to solve this type of questions, once you know the G star values, finding the angle between the any plane, angle between the any direction, magnitude of the any directions,
interplanar spacing between the planes, everything can be done just by using the G star. That is a metric tensor in the reciprocal space. And that's all. We have solved this particular question number 9. Okay. Just please let me know if you have any doubt in this particular session that we have discussed.
Hello,
Yeah.
hello.
Yeah. Please let me know.
Can you please means can you please understand me once, because I'm not able to understand this particular question.
Question number 9. This one, right?
Yeah, yeah.
Okay. Yeah.
Yes.
Yeah. So here, what question was telling us that there is a orthorhombic system. We have the orthorhombic system whose A, B, and C was given to us, and we know that they are not equal to each other. And for orthorhombic, we also know that alpha is equal to the beta is equal to the 90 degree. Sorry, also gamma will be equal to the 90 degree in this case. The question number 1 is telling us to find the reciprocal metric tensor. That is, we need to find this reciprocal metric tensor. A star dot A star, B star dot A star dot B star, and A star dot C star. So on and so forth we have to find. So let's try to visualize it, how A star, B star, and C star will look like. Right now I am just drawing for the real space. That is A, B, and C I am drawing. And we know they are perpendicular with each other. What is the A star? A star is, we can write B cross C divided by volume. So the B star, the direction of the B star will lie along the B cross C. Let us do the cross product B and C. What we will get, the cross product will be nothing, it will be along A direction, right? This part you have got till now.
Yeah.
Yeah. Okay. So what we can say, it will be along the A. So what we can say that, and the cross product between B and C will be nothing but they are 90. So it will be B and C only. Sine 90 is 1. And the volume, V is a volume of the
Yeah.
orthorhombic. Yeah, it will be A, B, and C. So what we can say, we are getting A star to be as the 1 upon A.
Yes.
The thing which we discussed that A star will lie along A, right? A star will lie along A because it is B cross C. B cross C, it will lie along A. Similar manner, B star will lie along the B for the orthorhombic. It will not happen in the case of triclinic or monoclinic systems. Okay, little bit evolved, rhomboidal system. That A star is lying along the A only, B star is lying along the B only. No, it will happen only for the orthorhombic, orthogonal system, Cartesian type of system, that is cubic, tetragonal, and the orthorhombic system, C star. Okay, so look over here. That is the, let me complete this first. B star dot A star and B star dot B star and B star dot C star. C star dot A star, C star dot B star, and C star dot C star. Okay, look over here. So here what we can say, that what is the cross product between dot product between A star and B star? That is A star, B star, cos of angle between them. What is the angle between A star and B star? This is A star, this is B star, it is 90. Since it is 90,
90 degree. Yeah.
it will be 0.
It's 0.
So this
Yeah.
entire term will go.
Rest I understood. Actually, this point I didn't get. So, can you please explain a little bit, like if it is like triclinic, so how will the A star will look like, in which direction? Can you please a little bit
Yeah. See,
elaborate?
let us say we are going with the triclinic system.
This is A star, sorry, this is A, this is B, and this is C. They are not 90 degree, they are not perpendicular with each other. So let's try to find the A star. That is, it will be perpendicular to the B and C. So perpendicular to the B and C. Okay. So let us say our B and C, the cross product will look perpendicular to them. This is a plane along the perpendicular to this plane containing of the B and C. We will get the A star. Perpendicular plane A and B, consisting of the plane A and B, we will get the C star. And perpendicular to the A and C, we will get B star, and it will be somewhere over here, let us say. And none of them in the triclinic cell. See, if we are doing the cross product of B and C, it will be normal to the B and C only. And so it will not be along the A because the angle between AB and AC are not 90 degree with each other. Okay, and that's how it is. For example, let us how to visualize it. This is an orthogonal system which we are taking. Let us say this is A, this is B, sorry, and this is A, and this is C. Okay, try to what we will get the cross product of A and B in the orthogonal, it will be along the A only. But what will happen? Let us say we are fixing our B and C over here only, and now we are stretching it onto the pulling the A face over here, pulling this particular face over here. So now what will happen? This angle will be distorted. It will not be 90 degree with each other. But the B and C cross product still will be perpendicular to B and C cross product still will be perpendicular to the particular face. And A is not on particular direction, on that particular direction. The most easy example for this is the monoclinic system. Okay, where the one of the angle is 120 degree. Okay, I hope it is clear.
Yeah, thank you so much.
Because in the monoclinic system, we know that the remaining part are the 90 degree with each other. This is A, this is B, and this is C. Remaining part are 90 degree with each other. If I take the cross product of B and C, it will be perpendicular to the B and C. So how it will go? It will go in such a manner that it will go along this, which will be perpendicular to the B also, which will be perpendicular to the C also. That this will be the A star. And we can see A star and A, they are not along the same direction. Accidentally, the symmetry of the orthogonal is in such a way that the A star is along the A only. Similarly for the tetragonal and the cubic system also. Okay, so that's how we have solved this entire thing. Okay, I hope there is no. Yeah, please let me know if there is any doubt. If this is yeah,
Yes, thank you.
it's clear, right? Okay, yeah, that's great. And so with this, we have finished our today's live session. Please try to solve the questions of the assignments. You will find that all the assignments questions will be very easy compared to the question that we have solved over here. Focus on the finding the G star, how you can find the metric tensor, how you can find the coordinate transformation matrix, general coordinate transformation matrix, that is Q, and how you can find in the reciprocal space. And the property that is the G star and Q, they are reciprocal of each other. If you find the matrix of the G, just invert it, you will get the G star. You find the Q, you will just invert it, find the inverse of that particular matrix, you will get the Q star in the reciprocal space.
One thing I would like to add over here is that the D spacing, the spacing which we have found just now, it is in the reciprocal space. So we know that how we can convert something from reciprocal space to the real space, the length, right? Since the length was in the reciprocal space that we have found, we just have to invert it. That is 1 upon that particular length, and we will get the interplanar spacing in the real space.